All right, what do we have here for part B? We're going to mix things up and do a natural log function. Be good. The natural log of 1 plus x equals the Taylor series right there, x minus 1/2 x squared plus 1/3 x to the third minus dot 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 plus, and now we see something interesting, negative 1 raised to the n plus 1 over n times x to the n, and then it would continue from there plus dot dot dot. So again, really nice. They just tell us that formula for the different terms. I mean, I think, kind of the thinking is we could reproduce this, these first three, let's say, using the Taylor polynomial style from the last section. But, could we produce enough where then we could then guess what that formula is for the general term, right? Well, luckily, we're not going to have to figure out that pattern ourselves. They just tell it to us. Really cool. Okay, so what's going on here? And especially that like negative 1 raised to the n plus 1, what's that from? Notice the terms here are not always being added. We've got positive, negative, positive. The next one will be subtracted. And then so, if they're going positive, negative, positive, then we somewhere in there is going to be negative 1 raised, and in this case it's raised to the n plus 1. So if n is an even number, then we're going to get what a negative term. So like if it's a square, a 2, then we end up with a negative. But if n is odd, then when we add 1, we end up getting a positive when this is done. So like the first term here, we would square, we end up with just a positive 1 when we do that. So we call this type of series an alternating series when it goes positive, negative, just kind of a side note. That's what that part is connected with. All right, let's talk about the nth term. So there it is. We need to take the coefficient of the nth term, right? Just the negative 1 raised to the n plus 1 over n. And of course, once we identify the coefficient of the nth term, then we want to find the next coefficient, a n plus 1. What do? Well, wherever we see n, we replace it with n plus 1, in this case twice. And then we'll simplify, so we'll have negative 1 raised to the n plus 2 over n plus 1. All right, once we have our an term and our an plus 1 term, then we're going to go and look at the limit as n approaches infinity for the absolute value of an plus 1 divided by an. And you notice in this second example, I've just gone ahead and done, the multiply by the reciprocal. So there's an plus 1 times, and I flip an right there to get started. Please feel free to just do this as your first step. Just flip that an over and multiply, because we're going to cancel some things out. Okay, so you see my first step here with this limit, and what happened there from there to there. So it turns out these negative 1s raised to the power can just vanish, and it's not really that they cancel out. That's not what's going on. It's the fact that we've got the absolute value. Okay, so either this is going to be positive 1 or negative 1, right? For different values of n. Same thing here. Well, when we take the absolute value, it's just going to make everything positive, right? So if it makes everything positive, this is just 1 and 1. And I can write that as n over n plus 1. Limit as n goes to infinity, absolute value. I'll keep the absolute value symbols there, but I'll know that any negatives are just going to vanish. So they're just annihilated sort of thing. Okay, now let's look at the limit as n goes to infinity. Think, okay, n over n plus 1. Well, as it is, if I was to put infinity there and there, Wouldn't this work out to be infinity over infinity? And yeah, hey, do you remember cases like that? That's called an indeterminate form. We cannot determine the answer of infinity over infinity. We need some help. So this goes way back. I forget exactly when we did it, but it was toward the beginning of the semester. If you have an indeterminate form like infinity over infinity, you need L'Hopital's rule. Oh, man. Okay. Performing L'Hopital's rule. We don't see it a whole lot in our class, so let me remind you how this works. But it's going to do the trick for us real quick. We put the L'(h) over the equal sign. That means we're going to perform L'Hopital's rule from here to here. We take the derivative of numerator and denominator separately. So the derivative of n is 1. The derivative of n plus 1 is 1. We took the derivative of the numerator divided by the derivative of the denominator. And well, 1 over 1 is 1, so that's the answer to our limit. And again, we got a positive finite answer. So we would take the reciprocal. Well, the reciprocal of 1 is still 1. So our interval of convergence here is from -1 to 1. Pretty cool. So just kind of reflecting, it'd be so much more interesting if we were in class together and we could, graph this, and we could graph, several terms here and compare them. Turns out that this graph and this graph are going to be almost identical between -1 and 1. So when x is between -1 and 1, this graph, and the more terms you get, the better. Model this thing really, 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 really well. But as soon as you stray outside of -1 to +1, then we say they diverge, that this one departs, and there's a, they go their separate ways, if you will. So if you were to plug in values of x between -1 and 1, across the whole thing, then these would equal each other if you went out infinitely far. Okay. Hey, we've got one last example. We did a rational function. We did a natural log. It's time for e. How about e raised to the 2x? And again, really nice. They just tell us what the Taylor series is. Of course, we could reproduce, several of these using Taylor polynomials. But we really are after this guy, right? We don't want to have to guess the pattern. Although this one's not too bad. 2 squared, 2 factorial, 2 to the third, 3 factorial, that sort of thing. Okay, there it is. E to the 2x. The Taylor series is 1 plus 2x plus 2 squared over 2 x squared plus 2 to the third over 3 factorial x to the third plus ... And you see the nth term there, 2 to the n over n factorial x to the n plus ... Okay, so well, there's our nth term. 2 to the n over n factorial. So we'll start with that. We want the n plus 1th term. So replace the n, both of them, with n plus 1, right? And you notice here, we've got that factorial involved. With any e function, the factorial is going to be part of your nth term or your Taylor series. Okay, so it'll be good to talk through this one. How exactly is it going to simplify, right? When we take the ratio. So, well, let's see. Okay. Here we go. So I've got the limit as n goes to infinity, the absolute value. I've got the n plus 1 term, 2 to the n plus 1 over n plus 1 factorial. And I'll multiply, and I'll go ahead and just flip the an term, n factorial over 2 to the n. Okay, so how's this going to simplify? Well, we can do that same trick we did a couple problems back with 2 to the n plus 1, right? That's 2 to the n times 2 to the first. And we'll get 2 to the n to cancel out. But what about the factorials? N factorial and n plus 1 factorial. How is that going to simplify? Well, you can see my work there, but let me explain. Let's look at maybe, for example, 5 factorial. That's 5 times 4 times 3 times 2 times 1. Hey, isn't that the same as 5 times 4 factorial? So I could take like that first number off and multiply just by the factorial of what's left. Okay, so if I've got n plus 1 factorial, then I could think of that as n plus 1 times n factorial. Right? I mean, wouldn't it be, if we saw it all written out, n plus 1 times n minus 1 times n minus 2, and I would keep counting down until I got to the end, you know, whatever the value of n was. Well, isn't all of that n factorial? And yeah, kind of same idea. So n plus 1 factorial is n plus 1 times n factorial. And what happens there? N factorials cancel out. Boom. So what's left after all my canceling? Just 2 over n plus 1. Limit as n goes to infinity. Got my absolute values, of course. Okay. Well, as n goes to infinity, what's going to happen here? You notice, well, n only appears in the denominator. The denominator is going to infinity, so 2 divided by infinity is going to approach 0. And I believe that was the second case back in our theorem. If the limit is equal to 0, what does that mean for the interval of convergence? It is everything. Every value of x will converge. The idea is this limit always converges. It converges to 0. So no matter what the value of x, if that limit converges to 0, then your series will always converge. Doesn't matter what the value of x. So if we go back, if we reflect, this function, no matter what value of x you pick, is always going to equal this infinite series. Positive, negative, 0, doesn't matter. Okay, hey, that does it for 10.2. Go check out the homework. See you in the live meeting.